obstacle, I guess.
Can you try now, Giovanni?
Yeah, now it works.
Okay.
Good. Okay, so we have now waited for 5 minutes, so I think it is time to get started. So welcome all. This is a demo tutorial that Bhupinder will be given today, and as mentioned earlier, it will be recorded and the recording will be made available. The topic of the tutorial is related to the DESDEO development, our open source software framework DESDEO, and in particular the evolutionary algorithms part of DESDEO. So please, Bhupinder, go ahead.
Hi. So today's topic is more focused towards the evolutionary algorithms within DESDEO and how they have been implemented and how we can use them to solve multi-objective optimization problems. This is a demo tutorial, so this will be a bit more on the general side for the general audience. Previously, different people have given more comprehensive DESDEO tutorials on various parts of the DESDEO framework. I will be talking more about that later in the talk. So if you need more details, all of these slides and many previous tutorials are available on our website, which I will also be sharing later on. However, let's get started with the topic of today, which is I will briefly introduce multi-objective optimization, like what it is, how many different kinds of multi-objective optimizations do we deal with. Then I will more specifically talk about evolutionary algorithms, which are one of the ways to solve multi-objective optimization problems. I will talk about desdeo-emo a bit, and then I will move on to interactive optimization using these evolutionary algorithms. But what is multi-objective optimization? I think everyone here already knows what this is, but I will just go over it briefly, just to be sure. Multi-objective optimization problem is a problem where we have multiple objectives which need to be optimized simultaneously. However, these objectives might conflict with each other, and due to which trade-offs might exist. If you try to make one of the objectives better, the other objective might get slightly worse. For example, on the right-hand side here, we see a graph where on the x-axis we have the price of some cards, and on the y-axis we have the top speed of some cards. And there are some cards in the graph. On one hand, we have this beetle, which is a lower price, but also a lower top speed. On the other hand, we have this Bugatti Veyron, which is very fast, but also very pricey. We would like to buy something that is cheap, but also something which is fast, but we cannot have both. We have to have certain compromises here. And there are certain cards which, for example, this Hummer here is very pricey, but is also very slow. And if the person who is buying these cars is only interested in price and top speed, they might not be that interested in a Hummer because there are other cars that are slightly cheaper and also slightly faster. So the aim of any algorithm that tries to solve these multi-objective optimization problem is to find out these set of solutions which try to optimize both of these objectives as well as possible. And there are always a set of solutions that satisfy this criteria, not just a single solution. There are many algorithms that try to find a representative set of all of these Pareto optimal solutions. On the other hand, there are certain other algorithms that only try to focus on small regions of these Pareto optimal solutions instead of trying to cover the entire region. Evolutionary algorithms are one popular way to solve these multi-objective optimization problems. And there are many kinds of evolutionary algorithms that also try to cover this entire region. There are some which only focus on smaller regions, but we will come back to that later on during this talk. Right now, let me give you an example problem. Let's say we have two objectives, y1 and y2, which are dependent upon two variables, x1 and x2. X1 and x2 are limited between 0 and 1 in this particular problem. And we say that x1 and x2 together form the decision space. This is the space that we can control. We can change these variables so that the objectives of our problem can change. And I have deliberately chosen these two functions so that they are conflicting in nature. For example, if I try to plot them on a scatter plot, I can plot the decision space here in 2 dimensions, and I have sampled some 100 points out of this decision space randomly. And if I try to map all of these 100 points to the objective space, we can see that it also covers a certain region of the objective space. Now, the goal of this problem is to minimize y1 and y2. If we look at one of these axes now in the objective space, let's say we try to minimize y1, which is on axis 1. So we can visually see that this solution probably is the best solution according to y1. It has the minimum value of close to 0. However, we can see that for the second objective, axis 2, it has about a middling level of value. In fact, the best solution according to y2 is somewhere here, which also has a close to 0 value for y2. But for y1, it has a very high value. In fact, any of these solutions along this line here are like either good in y1 and bad in y2 compared to any other solution along this line. And therefore, we can say that all of these solutions here are Pareto optimal, and the goal of any multi-objective optimization problem is to find solutions from this edge of this space here, and therefore find out the values in the decision space that are responsible for those solutions. So what is the DESDEO framework? The DESDEO framework is a collection of open source tools which we have developed to solve multi-objective optimization problems. This entire framework is focused towards something called interactive optimization, which I will talk about later in the talk, and data-driven optimization, which again will come up later in the talk. There are many methods implemented within the framework, including evolutionary algorithms and many other scalarization-based approaches, which I will not talk about during this talk, but there have been previous seminars on this, and the recordings of those seminars are available on our YouTube website. The framework also includes many benchmarking tools and visualization tools, which can help new users or researchers implement new algorithms, test those new algorithms, and see the results for themselves. As I said, this is an open source framework. So if you go to our GitHub website, you will be able to find all of the code associated with the DESDEO framework. Here, I'm only showing some of the more essential packages within the framework. However, we have other packages, for example, a package for a graphical user interface, which I have not mentioned here. But as I'm showing right now, there are some focused packages within the DESDEO framework. For example, we have this desdeo-emo package, which is specifically designed for evolutionary algorithms. There are other packages which help us implement multi-objective optimization problems, or other packages that contains tools of which we can use during optimization. And the other scalarization-based algorithms that I mentioned, all of them are contained within this DESDEO MCDM package. So how do we implement a problem within the DESDEO framework? Well, as I said, many talks have been given in the past that go into much detail about how to implement a problem within the DESDEO framework. I would ask you to check out this talk in particular, which is on YouTube. And it goes into detail about how the various classes within a DESDEO problem and how you can use them to implement any kind of problem that you want. I will be presenting some examples of some simple examples later in the talk when we try to solve these problems using evolutionary algorithms. There are also documentation available on this website. You can check those out as well as various Jupyter notebooks, including the one that I'm showing right now on our various GitHub repositories. So this has been the introduction. Let me move on to evolutionary algorithms now. So evolutionary algorithms are population-based optimizers. They are inspired from nature, and they conduct optimization using a population of solutions, which we call individuals. So these solutions represent some, at least during the initial parts of the optimization, a random set of values for these decision variables that I talked about. And many of these solutions sometimes combine with each other, share their properties, share their decision variables, and create new solutions, which we call offsprings. This happens over a number of generations. Every generation, these individuals combine together and form new offsprings. These new offsprings are then evaluated, which means that we calculate the objective values for these new offsprings. And then we apply a selection operator. The job of this selection operator is to kill off the bad individuals and keep the more optimal individuals alive. So in any given generation, some of these individuals die, and basically we have the survival of the fittest here. And over multiple generations, slowly and slowly, we come closer and closer to the Pareto front. So how does an evolutionary algorithm work? In general, we have two basic steps. First, we have the initialization, and then we have a set of steps that happen within a generation. And this generation loop is repeated again and again for as long as we want. At the start of each generation, we create some offsprings, we evaluate those offsprings, and then we do the selection step for the next generation. Now, if you look into the code, we have these exact steps represented in a pretty one-to-one fashion. We have the initialization step in the code. This code, you will find a more complicated version of this code with the desdeo-emo, where in the initialization step, we initialize the population using the population class that we have. The population class is an abstraction of all possible things that we should be able to do with a population. For example, combining various individuals to form new individuals, or keeping track of the populations, killing some individuals or keeping some other individuals alive, or evaluating new solutions. All of these things can be done with the help of this population class. We also initialize the selection operator. Now, as I said, there are many evolutionary algorithms, and many of them might use the same way to create new offsprings, or depending upon the problem formulation, they will use the same way to evaluate these offsprings. However, the selection step might be the only thing that varies between these uh, uh, evolutionary algorithms. So therefore, we also implement many different selection operators within the framework, and you are able to select any of the selection operators for your own algorithm. These have been implemented in a very modular fashion. In all of these classes, we also have this next gen function, which basically implements one generation of the evolutionary algorithms. And as you see, the first step in any generation here is the creation of new springs, which we can do using this population class. We have this mate method in population class, which can be used to create new offsprings by combining the previous individuals. Then we have this add methods that evaluates these new offsprings and adds it to the population that we have. And then we have the selection operator that I previously mentioned, which we can use to kill off the bad individuals and keep the optimal individuals alive. And to keep them alive, we have this keep method in this population class, which can be used to keep only a certain subset of the population alive. We also have other methods, such as the delete method, which is the opposite of this keep method. There is evaluate and many other methods within the population class. However, this is a very simple evolutionary algorithms. And if we look at the literature, things can get a bit more complicated. For example, there are many algorithms that group together these generations into a set. And at the beginning of the set of generations, they try to set certain parameters. And then once that set is over, they might try to update those parameters. For example, as the optimization goes forward, they might want to change these parameters a few generations at a time. To represent a structure like that, we make this structure a bit more complicated. We still have the initialization and this loop of generations, but this loop of generation now happens inside this iteration loops. And below this, before this generation loop, at the beginning of each iteration, we might have some pre-iteration steps. And at the end of this set of generations, we might have some post-iteration steps. And this again is represented in the code with methods that have very obvious names. For example, we have this iterate method, and all it does is run some pre-iteration code, then runs the next generation for a few generations, and then runs the post-iteration code. And what these pre-iteration and post-iteration methods do is dependent upon the algorithm. For example, we might want to archive certain solutions over time. That can be done in, for example, the pre-iteration part of the loop. We might want to set certain parameters. That can be done here. We might want to visualize some things or calculate certain metrics. All of these things can be done in these post and pre-iteration methods. Finally, we also have a termination criterion. This termination criteria can be, for example, a total number of generations to do this optimization over. Or this can be a total number of function calls, or this can be whether a certain metric value has been reached or not. All of these things can be implemented within all of these different kinds of metrics can be implemented within the method as well. So let's see an example of how to implement the simple problem that I showed earlier and how to optimize it using DESDEO. On the left-hand side here, we see some code. The first few lines basically import some important packages which we need to implement this problem. For example, this variable builder function from desdeo problem can be used to create the decision space. So we can define every single thing about the decision space that we need using this variable builder, which we do here in these next few lines here. We have two variables, as I showed before. Let's give them name x1 and x2. And the lower and upper bounds of those variables, as defined before, is between 0 and 1. We also have to set some initial values for these two variables. These values are not used in evolutionary algorithms, but the other methods that I described earlier might need to use some initial values, and therefore we need to provide these values here. Then we can define the mathematical functions that define the objectives. We had two objectives, and both of those two objectives can be defined inside a single Python function as defined here. And once we have this Python function, we can formally implement it within desdeo using this vector objective class. And all this does is it takes the Python function that we just defined, and we just give some names to the objectives. We have two objectives here, so we might as well give them names y1 and y2. And once we have the variables and the objectives, our definition is almost complete. We can wrap everything together using this emo problem or multi-objective problem class. All we need to do is to provide the objectives and the variables. And based on that, we now have a problem class. This problem class can be used to evaluate new solutions. For example, here we evaluate this solution where x1 is equal to 0.5 and x2 is equal to 0.7. And if we print out the result, we can see that the results are not just the objective values. There are many things being returned here. One of them are the objective values, and they are the values that these functions returned. And then we have some constraint validation values. So constraints are something that I have not described yet. However, we have already seen a kind of constraint here. For example, these x1 and x2 values are constrained between 0 and 1. That is one kind of constraint called bound constraints. However, there can be other kinds of constraints, more complicated formula for constraints. For example, let's say we did not want the sum of x1 and x2 to exceed a certain number. That can be a kind of constraint. And if those constraints were present, we would have some values here. The constraints can be defined in a very similar way to the objectives. Then we have this variable called fitness, which looks almost the same as the objectives here. So this is a decision that we made very early during the development of the desdeo-emo package, where we decided to have two different variables, objectives and fitnesses. And the evolutionary algorithm would deal not with these objective values directly, but with these fitness values directly. And what this helps us do is, let's say instead of minimizing both f1 and y1 and y2, if we wanted to maximize y2, one thing that a user could do is multiply this entire function with -1. That basically converts a maximization to a minimization. That is one way to solve that problem. The other way is to just implement it within the framework where we can just say that, okay, these are the true objectives. One of them have to be optimized. So inside the code, the correct objective is multiplied by -1, and in the fitness value, in the fitness here, that would be reflected. For example, something like that can be done by doing this. I just provided this new variable here, which is maximize. I'm saying that the first objective needs to be minimized, the second objective needs to be maximized. And we can see that these fitness values are reflected, the changes are reflected in these fitness values. However, this is too simple. Like someone could have done the same thing by multiplying this by -1. Why did we need to implement it within the code? Well, there are certain algorithms that might do something a bit more complicated than just multiply these values by -1. I will come back to that later in the presentation, but having this separate fitness values allow us the freedom to implement those complicated variations of certain algorithms pretty easily. Instead of re-implementing an entire algorithm, we can just implement a new way of calculating fitness, and we can just use the previous versions of the evolutionary algorithm to do the optimization. So now that we have this implementation of a problem, how do we go around and solving the problem? Well, the desdeo-emo package now has implementations of many evolutionary algorithms. For example, we currently have IPEA, MOEAD, NSJ3, and RBA supported within desdeo-emo. All of these are evolutionary algorithms that can solve multi-objective optimization problems. And even though I have only mentioned these 4 names, all of these algorithms have many, many variations, many of which are implemented within the framework. However, let's solve the problem that we just implemented. Let's use NSJ3. To solve the problem, all we need to do is to send this problem object that we just created. And if we wanted to, we could just end it here, do something like this, and the optimization would run just fine. However, we can also set some variables. For example, this is a pretty simple problem. Like these are just 2 linear functions. And I think that just having a population size of 10 is good enough. Let's run this for 10 iterations, and let's just have 3 generations per iteration. So a total of 30 generations. And let's make it so that this evolutionary algorithm keeps an archive of solutions over time. So if we run this, the way to do this is to first initialize the evolutionary algorithm, and then we run a number of iterations. The evolutionary algorithm provides this method called continue evolution, which just returns a Boolean variable that tells you whether you should continue evolution or not, whether a certain termination criteria has been reached or not. Because we have set the number of iterations and the number of generations here, this particular method will return true as long as we have not reached that number of iterations and number of generations. If there were some other criteria that we have defined, for example, a total number of function evaluations, this method would be reliant on those. And we can run iterations using the iterate method. And at the end, we can just run this evolver.end method that returns the solutions, the corresponding objective values, and the archive that we have asked this evolutionary algorithm to create. And if we run this, we can get a solution. We can get solutions that look like this. At the start, and here we are visualizing the objective space. At the start, the population is created randomly. These solutions look like they are all over the place. These are not even, we can clearly, because we are minimizing, only some of these solutions are even good. Most of these solutions are bad. However, if we see how these individuals evolve over iterations, we can see that some kind of optimization has happened. Over time, uh, all of these individuals try to come closer and closer and closer to the set of Pareto optimal solutions. And then this algorithm tries to spread these solutions apart um, in a more uniform fashion. And at the end of this step, we can see that this looks more or less similar to what we had wanted to achieve when we visualized the objective space maybe half an hour ago. And therefore, we have achieved a very simple optimization process here. However, this is a very simple problem with two mathematical functions. In real life, we might not have something like this. For example, what we might have instead is data. In many industries, all you have is data. The objectives themselves might be very complicated simulations, or it might just be some machine creating new products and just noting down what the qualities of those products are depending upon some shape of the product or some other variable controlled by that machine. And all we have are certain samples of those data. And we might have certain controlling variables or decision variables corresponding to each one of those samples. And we might have certain objectives that have been evaluated for those samples. So how do we use just this data to do some kind of optimization? Well, in DESDEO problem, we have this data problem class that is specifically created to handle data-driven problems. What this does is we can import this data set as a pandas data frame and simply pass the data set to this data problem class. And we can tell data problem that, okay, x1 and x2 in this data set are variables and y1 and y2 are the objectives. Now, what we can do is use machine learning algorithms to basically simulate the objectives. So instead of using some complicated simulation, or instead of asking the machine to create new products, we can instead use this data with machine learning algorithms. For example, here we are using something called Gaussian processes or kriging to simulate the behavior of y1 and y2. And to do that, we simply need to run this train method in the data problem class. And we can pass this machine learning algorithm to the train method, which tells it how to do this training. We can send a single machine learning algorithm here, or we can send one machine learning algorithm for each objective. So you can imagine one of them can be this kriging for y1, but for y2, we might want to use a neural network, or we might want to use something like an ensemble method, like random forest method, so on and so forth. Those things can be done using this train method. And if we look at the results now, the results, a new solution can be evaluated in almost the same way as the emo problem that we had defined earlier. In here, we evaluate the same solution as before. However, instead of just having the solution, we also have this new attribute called use surrogate, and we put the value there as true. If those values are true, then we use these machine learning algorithms to do the evaluation. However, if this was false, and if we had provided certain analytical functions within this data problem class as well, then those analytical functions would have been used for evaluation. Now, if we look at the previous implementation, we had the same solutions 0.5 and 0.7, which led to objective values of 0.6 and 0.4. If we look at the new data-driven implementation, we have the same decision variables here, but the objective values are slightly different. And that is something that we have to deal with in any data-driven problem. These values are not going to be 100% accurate. There will always be some uncertainty margin, some margin of error. And those margins are represented using these uncertainty values here. There are many different kinds of surrogate modeling techniques or machine learning techniques, some of which might also provide these uncertainty values. And if they do provide these uncertainty values, we report them. Now, if an evolutionary algorithm can make use of these uncertainty values, then it's very good. We are providing these solutions to those evolutionary algorithms. But if not, then these values can be ignored and optimization can be done simply based on the fitness values. And now that we have implemented this problem as a data-driven problem, all we need to do the optimization is the exact same thing as before. The code is the exact same, except we have this one additional variable, which is use surrogates. Again, if you put that value as true, then we do optimization using these models. And after that, the rest of the code is the exact same. And we can visualize the solutions again, and it looks more or less the same. Yeah, it looks almost exactly the same. The values themselves are slightly different because these are machine learning models, and there's a margin of error here. However, because this problem was so simple, the solutions that we get are almost exactly the real solutions. So this is how we do not just optimization, but also data-driven optimization. And finally, we can now move on to interactive optimization. So I showcased various Pareto fronts to you from the same problem, but one was an analytical formulation, the other one was a data-driven formulation. However, there were many solutions there, but at the end of the day, only one of them are going to be applied in real life. If you were buying a car, it's not like you are going to buy a Bugatti Veyron and a Beetle. Maybe you have enough money to buy both, but if you're financially responsible, you might only want to buy a single car. So how do you choose which car to use? And evolutionary algorithm might be able to tell you that, okay, maybe don't buy this Hummer if you only care about top speed and price. Buy either a Beetle or this Tesla or this Veyron. But how do you choose which one to buy? Well, in real life, you might have some preference. For example, you might say that, okay, a Bugatti Veyron might be a bit too expensive for me, so maybe I won't buy that. I can maybe buy either a Beetle or a Tesla, but a Tesla also has like a middle level of price, and I am able to afford that. So maybe I will go with that. So what I basically did here is make a decision. And at the end of any any optimization process, there is someone making a decision. And they might only be interested in one or a few of these solutions. The person who makes these decisions are called a decision maker. They might just be a single person, or they might be a group of people. And they might make a decision before the optimization process has even begun. If that's the case, we call that a priori optimization, and the optimization algorithm can take these preferences into consideration while doing the optimization. On the other hand, we can present all of these solutions to the decision maker and then ask them to make a choice. And that can be a posteriori optimization. The most simplest way of doing that is to just visualize all of these very optimal solutions and then hoping that the decision maker can choose one of them. But there are more sophisticated methods that support the decision maker in making decisions by making these choices a bit more simpler. However, the point of this talk is something called interactive optimization, where the decision maker is heavily involved during the optimization process. In an evolutionary algorithm, they might give a preference, and then we might be able to run a few generations, and they might be able to see what solutions it returns based on the preference. And based on these new solutions, they might change their preferences. And then we will run a few more generations and see how these new preferences changes the solutions. So I have already talked about this. A non-interactive optimization. In non-interactive optimization, we might give the decision maker something like these Pareto optimal solutions, hoping that they choose one of them. However, in real life, like a decision maker might not be able to choose like 1 out of 40 solutions in this case, or maybe 100 solutions in hundreds of solutions in a real problem. And the problem gets even more complicated if you have more than 2 objectives. How do you visualize 5 objectives to a decision maker? 5 objectives and 100 solutions, 10 objectives and 1,000 solutions. How do you visualize it? How do you expect a decision maker to make a choice in such cases, choosing 1 out of so many solutions? Moreover, I have been assuming that the optimization algorithm or the evolutionary algorithm is able to find these solutions. However, when the number of objectives becomes very high, it becomes more and more difficult to find a uniform spread of solutions along these Pareto optimal solutions. So instead, what we might choose to do is to do interactive optimization, where the evolutionary algorithm can use those preferences to focus only on a small region and return a small number of solutions based on which the decision maker can make some choices. What might those preferences look like? For example, a decision maker might say that, provide me some solutions that achieve certain objective levels, objective values. These values are called aspiration levels or reference points. And a decision maker might be too optimistic about these values because they don't really know at this point what Pareto optimal solutions exist, or they might be too pessimistic. Based on that, a method can return different kinds of solutions. For example, we still have these sets of Pareto optimal solutions, which now we can assume that the evolutionary algorithm does not know about all of these solutions. However, the evolutionary algorithm might know that, okay, a decision maker wants solutions that at least achieve this purple point here, which is 0.2 for the first objective and 0.4 for the second objective. Based on that information, the evolutionary algorithm might try to find all solutions that at least reach this value or become better. And in this plot here, all of these orange points are at least better than this purple point in at least one objective, or maybe even both. So in this case, the decision maker was too pessimistic about this particular preference that they gave. And the method was able to find many solutions that are even better than that. There are many optimization methods that might return one of these solutions rather than all of these. However, uh, the decision maker, because they only wanted to achieve a value of 0.2, 0.4, if they got a value of 0.1, 0.3, we can assume that they might be happy with the solution. If not, they can change their preference. And let's say they change their preference to this red point down here, which is a bit too optimistic. Based on that, all that we can do is to try to find solutions that either look like the preference that has been given or try to achieve these values as well as possible. And in this case, the evolutionary algorithm returned these green solutions here. There might be methods that only return one or a few of these solutions, or there might be some other algorithms that try to find all of these green solutions. But that is just one way to provide preferences. There might be some other ways. For example, a decision maker might see some solutions during this interactive process, and they may say that, okay, I like this one solution, and during some other iteration, they like some other solution, and later on, they might say that, okay, give me solutions that look like these two again in a new iteration. Like, give me some solutions around these solutions. And that might look something like this. For example, let's say we just have this purple solution here. At some point, this was discovered, and the decision maker might want more solutions that look like this. So the algorithm might return solutions nearby. And at some other point, the decision maker might say that, okay, give me some solutions in this region. And the algorithm might return solutions that look like this. Or in an iteration, a decision maker might say that, okay, give me solutions that look like both of these two solutions. And the algorithm, different algorithms can handle these kind of preferences differently. One algorithm might return this green set and this red set. Some other algorithm might return all of the solutions in between the two solutions that we just, that the decision maker was interested in. So the same kind of preference can be handled in different ways. And in desdeo-emo, we provide all of these ways that I just described and many, many more. So how to do this interactive optimization? In fact, we don't really need to change the code at all. If you remember from the previous implementation, the code looks almost the same. We have created this problem in a very similar way, in the exact same way as the analytical formulation. Excuse me. And we set these parameters in the exact same way. At the end, we add this one variable here, which makes this optimization interactive. And that is interact is equal to true. We can do this in NSJ3, we can do this in RVEA, we can do this in some other algorithms within the framework as well. And what does that allow us to do? Well, we can check what kinds of interactions are allowed by checking out this variable called allowable interaction types. And that returns a dictionary with a set of keys. The first key here is a reference point, which is the same as the aspiration level I talked about. And based on this reference point, you can read some text here, and this text basically tells you how this evolutionary algorithm is expected to use this preference and what kind of solutions can you expect out of the optimization process. If you don't want to give a reference point, you can instead choose some preferred solutions. You can choose one or more preferred solutions, and based on that, the evolutionary algorithm does something else. And you can read these details and see if you want to do this instead. Or you can say that, okay, instead of choosing which ones I like, it is easier for me to choose which ones I don't like. And that might be another way of providing these preferences. Finally, we might have something called preferred ranges, which is similar to a reference point, but instead of providing one value of which values you want to achieve, you basically provide a range of objective values, and these solutions should lie in between those ranges. So let's say we choose one of these as the uh, 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 the way to do interaction. And at this point, I think I will exit this presentation form and go into the code form, because this might be easier if I do it in the code form, because this is interactive. We might need to run these codes multiple times and see how the results change over time. So, for example, we start by setting the interaction type. And let's say we have chosen the interaction type to be a reference point. And we start the evolutionary optimization process in the exact same way. We run this start method, but now we see that the start method has returned two objects. One is a preference object, the other is a plotting object. The preference object can be used to provide preferences. The plotting object can be used to plot solutions. And if we run this, we see that the preference object contains a message. It is asking us to provide a reference point, which is worse than a certain value. And at this point in optimization, this is just the start. These solutions are almost random and nowhere close to the Pareto optimal solutions. Decision maker might look at these solutions and say that all of these solutions are bad. I don't want to give any preference here. Do some optimization and then come back to me. So we can achieve something like that by not providing any preference at all. We run the iterate method, and inside the iterate method, there is an option to provide a preference. But instead of doing that, we just pass none. And if we do that, we basically run the optimization process for a few generations without any preference. And if we do that, it tries to cover the entire Pareto front. And we might run this for a few iterations and see what the results look like. And at some point, the decision maker might get comfortable. Okay, now it looks slightly better to me. Maybe we can provide a reference point somewhere in this region. So somewhere close to this point here. So the decision maker might say that, okay, give me some more solutions near 0.4, 0.1. And to do that, we just put those values inside the preference object that we had received from the iterate method. Once we put it inside the preference object, we simply pass the preference object to the iterate method back. And we can just repeat the iterations and see what the solutions look like. So as you can see, in a single iteration, most of the solutions are now focused around this area where the preference was provided, 0.4, 0.1. And we can run this a bunch of times and see what the solutions look like. So after a few iterations where the same preference was provided, we can see the solutions are now very focused around this region. The decision maker might be happy with these solutions, or they might want to change the preference. For example, instead of 0.4, 0.1, what if they do 0.2, 0.3? Maybe they are trying to move around in various parts of the fronts and see how the results look like. So let's run this with the new preference. And as you can see, after one iteration, and if you remember, one iteration was just 3 generations, not a lot has changed, but we can see that the solutions are trying to move over to a different part of the front. If we run this a few more times, over a few iterations, we can see that the solutions are now close to a different part of the front, closer to where the new preferences were provided. And maybe the decision maker might be happy here, and they might choose one of these solutions as their solution. Alternatively, we can try to use a different kind of preference. And instead of relying on an evolutionary algorithm to do this interaction, what we might do is change the problem formulation a bit, perhaps. Maybe incorporate the preferences directly in the problem formulation. One way of doing that is something called IOPS. We have published papers on this particular topic. And basically, this allows us to make any evolutionary algorithm interactive by putting the preferences in the problem formulation itself. And one of the ways to provide the preferences for IOPS might be to choose multiple solutions or to choose multiple reference points. And what IOPS would try to do is to find solutions within in between these reference points or in between these solutions. But what is the result of something like that? For example, I might try to run IOPS problem dot evaluate and maybe array 0.5, 0.7. This solution is the exact same as what we had seen before. And if we try to run this, let's make it look slightly better. Yes. So if we look at the evaluation of this solution, the objective values are the exact same as what we saw before. However, the fitness values are different. And that is how we implement this particular preference within the problem formulation itself. The objective values are themselves not being changed, but the fitness values are being changed. And based on what these values are and what the preferences were, these values might be good or they might be bad. If I change this to 0.5, 0.2, I might have some other result here. Why is this infinity? Maybe it's because of there might be an error in the code here. This is pretty this is a pretty recent implementation, so there might be a few bugs. I will check the code to see if this is the correct value of the fitness or not. However, let's see if the algorithm actually works or not. Maybe it will work just fine even with that. We can pass this problem to some evolutionary algorithm, and the evolutionary algorithm, because it deals with these fitness values, it will be able to do this optimization without any additional changes to the algorithm itself. So we can run this, and we run this using the exact same parameters as same parameters as before, except I have increased the population size here because we can see what the solutions look like here. In here, we have provided preference where one of the reference point is provide me solutions between 0.1 and 0.4, and the other one is and the other reference point is 0.45, 0.05. And the solutions here are not following the preferences. This is my bad. This is one of the issues with live demonstrations. Things might go wrong. Things are going wrong here because instead of the solutions being written in this region, I wanted the solutions to be written in this particular region here. And that is not happening. I will have to check why the second fitness values are wrong. But we might change that by instead doing just changing what this formulation looks like. And we can do that using let's see. Yeah, this might work. So this is another kind of IOPS formulation where instead of giving 2 reference points, we just give a single reference point. And if we try to run optimization on that, so let's give just a single reference point. And see what the results look like in that case. Let's give a point 0.05, 0.3, for example. So in this case, we wanted to find solutions that come close to this aspiration level of 0.45, 0.3. And that point lies somewhere here, 0.45, 0.3. And we can see that this evolutionary algorithm has resulted in solutions that are almost all of them are better than what we had hoped to achieve. But if we give a point like 0.1, 0.3, yes, we might give a reference point that is a bit too optimistic. And in cases like that, where the reference point lies somewhere here, the algorithm is still able to find solutions that come as close as possible to the given preference. And that is how we do interactive optimization. We repeat this over multiple iterations, and as soon as the decision maker is happy, we can stop the interaction process. And at this point, I will stop presenting my own code and open this talk to any questions that you might have about implementation, about various algorithms, or about how to implement new algorithms.
Thank you very much, Bhupinder. Who would like to ask first? Or maybe we should stop the recording. Would it be then more convenient to ask?
We can stop the recording.